All right, so a little bit about me. Here are my contact details. If you want to reach out, I'm a security researcher at a company called Vector AI. And what we do is threat hunting in on-prem networks and the cloud. And we do that using artificial intelligence. So check us out. Before that, I worked as a pen tester and researcher with the X-Force ethical hacking team at IBM Security. And before that, spent a long time designing and developing software. My interests are diverse. I'm really interested in a lot of things about security. Probably my primary passion is reverse engineering and binary exploitation. Because of my software background, I'm interested in secure software development. Always happy to talk about that. Because of my day job, I do a lot of cloud and network threat detection work. And in my leisure time, CTF competitions, there's really nothing that can beat that. It's amazing. Love doing them. Just spending time with your friends and solving challenges. It's amazing. And I currently live in Ottawa. Originally, I'm from Russia. So, agenda. So we'll start talking about what reverse engineering is and its applications. What can you reverse and why do that? What are the legal issues associated with reversing? What are the different categories of reverse engineering? I'll go through a few code examples to make things easier to understand. I'll talk about tools that are available, which are plenty. There are, of course, some obstacles in doing reverse engineering, and I'll go into some detail on that. And then I'll kind of outline a plan for anyone who wants to start doing reverse engineering, how to start practicing, and what the general strategies are. And I'll wrap up with some resources and takeaways. So what is reverse engineering? So the definition is, so reverse engineering, or reversing as it's sometimes called, is basically a process of creating a blueprint of an object by analyzing it. So knowing nothing about it in advance. You're just looking at an object or event and kind of going backwards and trying to recreate its design. And the important part of this is that this has to be done because original design is not available for whatever reason. Maybe it was lost. Maybe it's just something you're trying to analyze is so old that it's just is not available anymore. Or the designs were intentionally withheld, as it's common in various commercial situations where competitors do not share designs of their products with each other. This is an important point because reverse engineering, as you can imagine, is a very labor-intensive activity. So really, there's no reason to do it if you have access to the original plans for something that you want to understand. Humans actually have been doing reverse engineering forever. So many inventions in human history have been analyzed and copied. And you can think about pretty much anything. Let's say invention of the wheel. If you think back about the person who invented the wheel, that person probably shared that design with their friends, with their tribe, but not necessarily with other tribes, and of course not with their enemies. And yet inventions like these, they just spread like wildfire throughout the human race. So what people do is, if somebody is unwilling to share knowledge of how to build something with them, they just observe and copy. And this is essentially reverse engineering. Also, if you think about it, all natural sciences are essentially reverse engineering. Nature doesn't come with a blueprint. So throughout the history, scientists had to painstakingly recreate the kind of design plans for nature. If you take physics or chemistry or biology, it's all a process of careful observation and analysis and kind of breaking things apart and understanding the different pieces and fitting them together and documenting. So essentially, reverse engineering. And if you have never done reverse engineering before, that's probably not quite true. I'm sure you've done reverse engineering without realizing it. So if imagine if you were a child and you're curious about the particular toy that you have, I'm sure once or twice you probably pulled your toy apart just to understand what's inside and what makes it make sound, or why are the lights flashing. And also in your older years, I'm sure you've attempted to fix some appliances around the home, not having access to the original blueprints, but you probably tried it anyway, maybe unsuccessfully. But that's essentially reverse engineering. You're kind of opening up something you're trying to understand and maybe fix, and you just proceed at doing that. There are a lot of modern uses for reverse engineering. This is a security conference, so of course security and vulnerability research is a primary reason for doing reverse engineering of existing products. But then there's pen testing, malware analysis. To be able to fight malware, you have to understand how it works. Of course, in military and intelligence work, reverse engineering is widespread because countries do not usually want to share their military inventions with each other, especially countries that are at odds with each other. So that's the work of the intelligence agencies, to actually spy on each other, discover these new technologies that their competitors or their adversaries are developing, and to try, if they're worth it, try to recreate them and replicate them back in their own country. Scientific research, I already mentioned that it's heavy on reverse engineering. Commercial research and product compatibility studies. So if you want to design a new product, I'm sure, and you're large enough corporation, I'm sure you have a research department that probably looks at products from your competitors, trying to understand how they work, and maybe take some innovations and replicate them. That would be beneficial for your product. There are some agencies, they do independent quality control. Consumer Reports in the United States comes to mind. They do testing of a lot of products, and I'm sure as part of that, they take products apart and look at how they're built and what's inside. So that's another use for reverse engineering. There is a whole line of business for some companies that do patent infringement detection. And what they do is they take chips from different companies, they're hired to do that, and they study how they're designed to spot patent violations, to see, let's say, pieces of code or microcircuitry that was actually lifted, and the ideas were lifted from competitors' products. So as you can see, there are lots and lots of uses for reverse engineering, and I'm sure there are more that I haven't mentioned. It's impossible to cover everything in this talk, so we'll only be talking about software reverse engineering. However, these days, that includes hardware as well, because much of modern hardware inside is driven by software. So that's kind of a description of why people usually do reverse engineering in the industry. Why would you personally do reverse engineering? Well, the problem is that a lot of software and hardware around us are black boxes. We have no idea what's inside. We don't know if these products are safe, if they're solid, and documentation and actual blueprints about how things are built are rarely made available if it's a commercial product. So there comes times where we want to be able to analyze products for their safety and quality. We want to look for security backdoors or security vulnerabilities. Sometimes you have a product that's so old that even the company that made it is out of business, and there's just nothing available about it, no documentation, no architectural plans, and it breaks, and you want to repair it. So you have to open it up and kind of study and try to figure out if there's maybe some component in there that's that failed, and that you want to maybe try and replace and fix the product. There is need to build compatible products. So let's say there are these Keurig cups that many of us use for coffee or tea. There are companies that started making these cups that fit into Keurig coffee makers or hot drink makers. But from what I heard, some of these companies, they did not have a license to do that. They just reverse engineered the design and started doing that. I think similar things have happened with printer cartridges. You want to, let's say, build cartridges that fit HP, Epson, and other printers, but build them cheaper and sell them cheaper, be a competitor to those companies. Those companies may not want to share their architectural plans with you, but you may want to do this anyway by just reverse engineering how these things actually are built. Sometimes you want to patch certain bugs in existing products or change behavior. Maybe you want to add new functionality to some device that you own. Reverse engineering would be useful for that. So basically, reverse engineering gives you that power. Something that was previously impossible, you thought you were dealing with this mysterious black box. Suddenly, you realize that if you know these techniques, you can actually go and open these things up and understand how they work. And there's this quote that I really like. Assembly, also software is open source. Basically, that kind of reflects that spirit that when you know how to do this, there are really no black boxes out there anymore. This is a security conference. I guess most of us here are in InfoSec one way or another. So I would argue that reverse engineering is actually a required skill if you want to be an InfoSec professional. And let me give you some examples. So if you look at all the vulnerabilities that are being announced for which CVEs are being issued, I would hazard a guess that most of them required some portion of reverse engineering to be done to either find the vulnerability or create an exploitation for it or do some other work for understanding it and documenting it. So if you want to do vulnerability analysis and bug hunting, you better acquire some reverse engineering skills. Pen testing. I was a pen tester before. We worked on an internal company pen testing team. And even in that situation, sometimes product teams are hesitant to share their product designs with you, and especially source code. So sometimes to hunt for bugs, you actually have to take a piece of software that your company produces and reverse it and try to understand if there are holes or backdoors inside. And that's for internal pen testing. If you are on contract to go to a customer site, I would think the situation would be even worse. Customers would probably be hesitant to open up the door for you to let you look at their source code, especially if that's not part of engagement. And for you to be able to look at some of the applications and see if there are holes inside, if there are some backdoors you can sneak through, is very, very beneficial to your job as a pen tester. Incident response. We had a case recently where we're helping a customer deal with ransomware infection. And what we had to do was we had to reverse that piece of ransomware to understand how it works and what different command control sites it needed to operate to get the full list of that. But also we found a kill switch inside, and we actually installed that kill switch on the customer computers to prevent further infections for that customer. So as you can see, there's immediate usefulness of having these skills in incident response, where you have to deal with malware, phishing, remote shells, command and control, everything. And last but not least, reverse engineering really can be a lot of fun. It gives you, sense of accomplishment, sense of discovery. You're overcoming challenges. You're kind of digging deep inside, discovering secrets. It's just exciting. And of course, it's not for everyone. Not everyone is that type of person. However, if you like putting together puzzles, solving crosswords, doing geocaching, all these activities, then I'm sure you'll find reverse engineering interesting. So what can you reverse? The answer is pretty much anything. The natively compiled executables for all platforms, compiled Java.NET Python portable code, mobile apps. On the websites, if you opened up any JavaScript lately, it's all minified and obfuscated, and some code is sometimes written in WebAssembly. All of that can be kind of pulled back and opened up and understood with reverse engineering techniques. You can analyze obfuscated PowerShell and Office scripting that's frequently used in phishing infections. Compiled automation scripts like AutoIt, AutoHotkey, and others. BIOS and bootloaders, malicious shell code, hardware, firmware. So you name it, it's probably possible to reverse engineer. Not everything is easily reverse engineered just because there may be physical challenges to overcome. For example, if you're dealing with a particular chip and you want to analyze the firmware, you have to have skills as a hardware engineer to first retrieve that piece of code that's stored on the chip. But then once you have that, you could apply software reverse engineering techniques to understand how it works. So before going further, let's talk about legal issues or potential legal issues surrounding reverse engineering. Big caveats, not a lawyer. I don't play one on TV even. And this is not legal advice. So just take everything with a kind of information with a grain of salt, but not if you have a legal issue or you suspect that you may get into legal trouble, please talk to professionals. So is reverse engineering legal? Like any big complex problem, the answer is it depends. So when you buy software or hardware, if you look at licensing agreements, I know most of us just, maybe throw them in the garbage, never look at them. But if you look closely, there actually, in most of them, there are anti-reverse engineering clauses. Vendors want to protect their intellectual property, and that's completely understandable. And actually, here are two snippets: one from Apple, one Apple iOS 14, and the other one from Windows 10. Just real examples of the language they put in these agreements. But I have a feeling sometimes vendors also want to kind of prevent people from digging in their software and maybe finding flaws and embarrassing them. There are a lot of existing legislation that actually protects software vendors from reverse engineering. There is DMCA, CFAA, there is copyright law, there are EU laws and directives, and I think there are other laws in other jurisdictions. So there's plenty of legal landscape to navigate. From what I read, as you're doing reverse engineering, you're probably on the safer side if you have legally acquired the product you're reverse engineering, because if you're doing that without paying for it, then legal matters get worse. So there are some clauses in the laws that are, I guess, more lenient to legal owners of either software or hardware that you're reversing. For example, in the copyright law, there is fair use defense that one could use, that if you do good faith security research, courts have determined that it's likely fair use that you can do. And there are other little exemptions here and there that allow some forms of reverse engineering to be done. So, for example, under DMCA, the legal owner of the product may reverse engineer it to circumvent some protections that software has in order to achieve interoperability with other products, for example. That's language in the law. And basically, as I mentioned, I'm not a lawyer. It's really hard for me to understand this, but from what I can gather, your intent, what you're trying to achieve as part of your reverse engineering efforts, and what you want to do with the information you discover are key in any kind of legal case. So you have to kind of before you go public with your research, you kind of have to evaluate your motivations and make sure that you will not get into trouble. There is a very good document that I found by Harvard Law School and Electronic Frontier Foundation that talks more about security research and legality of it, and it kind of does quotes the snippets from different laws that are available and discusses different situations that security researchers can get into as they try do security research on products and specifically reverse engineering. So I suggest you look it up. And by the way, I shared the slides in the chat, so you can find these links. You don't have to take snapshots of the screen or anything. All right. So to my layman's understanding, I divide the cases of reverse engineering in 3 categories. What's probably safe to do is reverse engineering of non-commercial code or anything you yourself produce. That's, of course, that's completely legal. Also, I would guess that if you take something and you just pull it apart to study, but do it in private, just for your own personal research, without going public, without taking advantage of the results, you're probably on the safe side. You shouldn't get any problems. And also malware analysis, because as long as you're safe, of course, as long as you have proper tools to do that and proper VMs configured, but you can analyze malware samples to heart's content, and I'm sure bad guys will not take you to court. The next stage is kind of more complex, and you need to tread carefully. If you do security analysis of commercial products in a public way, there are certain rules around that, and it's best to participate through bounty programs because they already have figured out proper legal ways of doing it. And also maybe as you do research, go through the, well, not maybe, it's actually a recommended way, go through a proper way of responsible vulnerability disclosure. You talk to the company, to their security department, you explain what you have found, and you agree with them that, yes, this is, let's say it's a valid issue, valid bug, company plans to do fix or a patch issued, and then after a certain grace period, you actually responsibly disclose the results of what you found. Publishing of tools based on reverse engineering discoveries also kind of can be a dangerous ground. You have to tread carefully. There actually were a few famous legal cases 20 years ago. John Johansson was arrested in 2000 for circumventing DVD copy protection. He built a tool or participated in building a tool that circumvented DVD copying schemes. In the end, was acquitted. Dmitriy was arrested after DEF CON in 2001 for circumventing Adobe ebook protections. Spent a few months in jail, but charges eventually were dropped. But even though there was happy ending there, you have to understand, some companies are happy to talk to security researchers and are happy to get vulnerability reports. Some are on the other way of the spectrum. They're really unhappy and they are really hostile. So even if what you're doing is completely legal, there may be a case where a particular company may just take you to court just to make your life harder, just to harass you. And they have deeper pockets than you. So be careful. Finally, really dangerous activity is just large-scale disclosures of everything you found, proprietary information, algorithms, or selling it, which is worse, or building compatible or competing products. Again, my understanding is that whenever a company is feeling threatened, that you are actually trying to threaten their livelihood to build a competitor to their product and damage their sales, they'll go at you and they'll take you to court. So be really careful with those cases. So there are 3 different types of reverse engineering you can do. One is data and communications analysis, and for that you basically are looking at proprietary data formats or network protocols which are not documented. This is more and more rare these days. It used to be very common, but still, some companies, they produce products, they do not document communication protocols or, let's say, storage structures for their databases and data files. And for that, you may need to look at the actual data that's produced. And it just requires careful experimentation. If you do not involve other types of reverse engineering, you can just look at data itself, or maybe the software just not available. You just use binary editors, capture tools to experiment and kind of figure out what the structure is. The next type is disassembly. And this is where you convert a compiled binary to human-readable code that's in machine language instructions. And there are 2 general categories. There's native code that's being executed by the actual processor, and there's P code or portable code. This is kind of a level above machine code. This is something that, let's say, Java or C# or Python compile their programs into, and that representation is more high level, is more portable, so you could take that, just like in case with Java, and execute it on many different machines. It's not tied to a particular hardware, to a particular machine architecture, and actually the interpreter on that machine on the fly converts that P code to native code. So that conversion is still happening. And there's decompilation. It's a process of actually attempting to recover original source code from compiled representation. Results are mixed for that because compilation by definition is a lossy process. So for native code, results depend on complexity of the application, and a lot of things can complicate that, and we'll talk a little later about that, what can complicate that. And C-like pseudocode can usually be recovered, but results really differ depending on what you're working with. But P code actually usually decompiles really well, and I'll show you some examples of that. There's also a difference between static and dynamic analysis. Static analysis, just by definition, you're looking at application source, you're not executing it, and it helps where the actual hardware that you need to run the application on is not available, and no emulators are available, no debuggers are available, or when anti-debugging measures are deployed that make that complicated. There's also dynamic, which allows you to analyze programs through execution and debugging. And it helps in cases where the actual generated code is obfuscated, compressed, encrypted, and by looking at it, you can really understand nothing. So this helps confirm insight gleaned from static analysis. Decompilers and disassemblers, by the way, often integrated with debuggers, so that helps with dynamic analysis. And really, in most cases, a combination approach is what works best. You really cannot do dynamic analysis without looking at the applications first, so you kind of have to do static analysis, and then doing just static analysis in all but some simple cases is probably tough unless you can do some kind of automation and scripting, because sometimes things are encoded, encrypted, really hidden really well, and you need help from a machine to open things up. You cannot do everything with a pen and paper. So let's look at a very simple example. So here is a very simple C application. By the way, do not, like, these samples that I'm going to show, they're horrible in the sense of secure software development practices. So do not take this code and implement things this way in your software. These are things I wanted to create samples that are related to security for demonstration purposes, but do not implement things this way in your software. So very simple program basically embeds password inside, checks what password was passed on the command line, and if two passwords match, great, returns 1, if not, returns 0. So very, very simple. So let's say we compile it, we run it, everything works, and then let's say we try to reverse it. And if you try to do that, if you try to look at compiled representation, it actually looks like just a bunch of garbage. It's really hard to understand. And I'm sure at this point some of you were, if you did this in the past, you were just discouraged and decided to drop it altogether. So decided that it's not worth it. Well, there is hope, because we can do the same thing, but actually disassemble the compiled representation. So again, this is our original program, but this is the assembly code that was generated, and it's disassembled from that compiled binary that I created. So if you look, things may still look hard to understand if you don't know assembly language, but I'm sure you would agree that they look a lot more encouraging than just a bunch of garbage. You can see that we have some kind of a translation happening here from one computer language to another. And if you look closely, you can actually see how different constructs get translated. So here, assignment of a password to a variable is translated to appropriate machine instruction. Then there's a comparison happening, and we're comparing to the value 2, and that's the same thing in assembly. There's a set of instructions that load a bunch of parameters and call the string compare function. There are results that are returned, 1 and 0. So as you learn more about this, this becomes more and more clear. With decompilation, things are even better. When you have a decompiler, you can get a much better picture of the code. Although quality may vary, you can see that with decompilation, you get a much better picture of what the original application was. You can see that you lose comments when you decompile. So the picture on the right was produced by a decompiler, Ghidra, and you lose variable names. Things look a little different. Things maybe moved around, but you can fairly easily understand what was actually going on in the original application. As I mentioned, in P-code-based languages, things are even better. They lend themselves very well to decompilation, and you have a Java example here on the top left, original application, on the bottom right, decompiled version, and it's almost the same thing. You can actually take it, compile it, and run it. So you could actually try it now. You could go and take, let's say, an Android application. There are tools to split it apart and extract Java code out of it, and you can reconstitute full original Java source code from it, or at least close to it. So that's very exciting if you know how to do that. Similar thing with .NET, another small program here that checks the password against an XORed array of bytes. And again, on the left is the original program, on the right, compiled representation. You can see that you lose, again, comments, you lose variable names. The program flow is a little different. Certain ifs maybe moved around a little bit, but the general idea is still there, and it's very easy to look at. So what are the tools that actually help you do that? So the primary tool that's sort of, I guess, synonymous with the reverse engineering is IDA Pro. Very famous, very widely used, tons of support for many processors and environments. Pretty much any chip out there you can take and you can analyze with this program written for that chip with this tool. Has a disassembler and debugger, and also has a decompiler add-on called Hexrace. It's really solid, really used widely. Has plugins, scripting, you name it. Unfortunately, it's very expensive. It's so for commercial license for just one architecture it would cost you from $2,000 to $4,000 US. So if you want to reverse, let's say, Windows executables and Linux executables, multiply that by 2. So that's it's you know, out of my range at least. But fortunately, there is a free version. It's kind of limited. You cannot do certain types of debugging. There is no decompiler, but it's free. So you can, and it's on Windows, Mac, and Linux. And also there's a home version. So if you're a professional that needs to use this, you can buy that. Ghidra, very interesting tool, was fairly recently open sourced by NSA of all organizations. Pretty solid. It's a little rough around the edges. I would say IDA Pro is much more polished. Also, many supported architectures, disassembler and decompiler. Unfortunately, it doesn't have debugger, but I think some groups are actually working on creating debuggers for it. Also has plugins, scripting, Python scripting inside. So these are really solid tools. And there is more. There are complete networks such as Radari with Cutter GUI. There's Binary Ninja. There are decompilers, returnable decompiler, and Snowman. And by the way, for all of these categories, you may as well add an ellipsis there because there are many other tools in these categories. It's impossible to list them all. But there are all kinds of different debuggers that are available that you can use. There are specialized tools for .NET, Java, Python, WebAssembly. So you have a lot of tools out there that can actually help you succeed in your reverse engineering efforts. And as I said, tools are too numerous. So it sounded pretty good so far, but now come the bad news. So first of all, a lot of information, just by definition, as part of compilation and optimization, is lost. So you're losing code comments, meaningful names of functions and variables, structure of some of the data structures, objects in object-oriented languages. Variables are moved by compiler between stack and registers, so it's very easy to kind of lose track of what different data value is stored and where at any given time. Execution flow constructs are obscured because compiler moved things around, so what looked like a loop before, because of the optimizations, may look like something slightly different, and it may confuse tools. So loops, conditional statements, exception handling, these are all things that complicate things. And also function inlining, embedding of libraries that just explodes the body of code. So the little tiny program that was 5 lines long that printed hello world and would have resulted in a very small and easy to understand executable, if you were to compile it with all the libraries it needed included in, it would explode to probably multiple megabytes, tens of thousands of lines of code, and it would be really hard to understand what's the functionality that's crucial for the actual application and what's just library code. And this is not all, because I'm just getting started. There are a lot of things that actually complicate reverse engineering. Software publishers know about reverse engineering, they're not happy about it, and they try to make reversers' life very hard. And there are many countermeasures that are deployed to complicate analysis. There's obfuscation. So there's a deliberate renaming of variables in scripting languages, P-code languages, so in languages that retain names. There are deliberate mangling of names to make it the analysis hard. There's code minification, where everything is kind of clumped together and it's hard to read. There's compression, so code and data are compressed in such a way that as program runs, it uncompresses them on the fly and runs them. And there are a lot of packers available out there. APX is one of them. So it's, as you can imagine, it's hard to look at an application like that. There's also encryption sometimes included with compression. So code and data are also decrypted at runtime, and there could be multiple levels of obfuscation and compression and encryption to make your life easier. It's like a nest and doll. And there's more. There are anti-disassembly methods where there are certain tricks you can do in assembly that confuse disassemblers and make it hard to understand. So it jumps into the middle of instruction, there are false branches, there's code that's self-modifying. Sometimes you can see it in shellcode, for example. It actually operates on itself and changes its own instructions to be able to bypass filters. As you can imagine, it's hard to analyze without careful debugging. Anti-decompilation also, there could be things that intentionally obscure proper program flow. Sometimes they execute jumps to registers, jumps to returns, calls and jumps, and other techniques. Useless and dead code gets inserted on purpose. Sometimes you can turn compiler optimization settings all the way up, and that way code gets optimized in such a way that registers are used as much as possible. All kinds of tricks are used in the generated assembly, and that makes it hard to decompile such applications. Some applications actually go to the extreme and use I don't know what the name is, but essentially these are tools that create a mini VM inside your application, compile your application code into a new language that only that VM understands, and that VM works as an interpreter for that language. So you now have a little piece of code that interprets this unknown language, and there is no disassembler for that language because it was just invented by the company that created that obfuscation tool. And there's some examples that you can look at. So it's really, these techniques are really tough to overcome, and yet there is more. So there are a lot of anti-debugging techniques. Applications embed code that detect debuggers and then act differently in the presence of debugger or exit altogether. There are ways to detect a VM. So if you're trying to analyze things like a malware in a VM, malware may exit early or do some damage. There is sporadic insertion of breakpoints, because if program just runs normally, breakpoints have no effect. But if you try to debug it, all of a sudden breakpoints start to mess with your debug flow. Sometimes they can use debug handlers to actually do execution, and that makes it hard to debug the sample. Sometimes there's signal-based execution, alarms, time-dependent code. It's just, you name it. It's not an exhaustive list, but it's an arms race. So the good debuggers and VMs can actually try and hide their presence. Disassemblers and decompilers can overcome some of these tricks, and there are deobfuscation compression tools available. So bottom line is, expect these challenges in your reverse engineering work. Know that they can all be overcome with adequate techniques and tools. There's nothing out there that cannot be reversed. It's just a question of how much time do you have, how much effort are you willing to spend. So how do you actually start out? If I haven't scared you by this point, so let's talk about how to actually start out. So the only way, as in anything in life, is to study and practice. There are certain things that skills that I think you need to get started. You have to have some beginner ability to write in a programming language. Most languages are fine, but C, C++, because of the closeness of how they are translated into the actual code, is an asset. Basic knowledge of your target computer architecture is a good thing to have. You have to kind of understand at least a little bit about how processor works, what registers are, what machine language instructions look like, how's memory organized. All of these will be helpful. And also a general idea of how compilers operate. It helps to understand how a high-level language, let's say like C, can be translated into a machine language. And you need this because you'll be doing the reverse process essentially. So it's good to be able to imagine what this sequence of machine language instructions, what they were originally when they were part of a C program. And of course, with this type of activity, you need attention to detail and patience. You can learn all of these things as you go, but I think you need some basic knowledge in order not to kind of stop and go all the time and look things up. So the next level is actually I recommend doing a do-it-yourself code sample. So you yourself can write and compile a few very simple programs that use different aspects of the language you want to learn how to reverse, and then open compile programs in different tools like decompilers, disassemblers, study different features, look at how compiled representation maps to original code, what code compiler adds, because compiler adds a lot of code. Your little hello world program actually has a lot of additional code added in there. There's setup, tear down. There like every function has a prologue and epilogue. There's library code. There's all kinds of stuff added in there to make that little hello world application run. So looking at that with a very simple example is really helpful. And also you can try debugging. That is going to be helpful as well. This way, why I suggest that you do this first is that this way you're taking one of the variables out of the equation because you know the end result of your efforts. You wrote the original program, so you know what the decompiled result should look like. Next level is to look at crackmes, and these are challenges designed by someone else, and there are lots of them out there. Typically, they're small applications. They're hiding some kind of secret, called a flag. The beauty of it is that you can download one and go at your own pace. If it takes you a week, fine. You're not in a hurry. A great resource for that is a website called WeChal. That's my personal recommendation. And the reason I recommend that is that because it's actually a directory of challenge sites. So it links to over 60 different sites with different CTF type challenges inside, and a fair bit of them have reversing challenges in them. So this is like a directory from which you can kind of branch out and go to individual sites. And they also have a global scoreboard if you want to kind of gamify your experience. Also, shout out to Ring Zero Online CTF. I think guys that built it are also helping with Hackfest's organization effort, and I've been using their site for a while. They have some great reversing challenges in there and other challenges, so check them out. So level 3, online and in-person competitions. You actually start doing CTFs, and there are all kinds of different CTFs out there from beginner to professional level. They occur all over the world regularly. And in pretty much almost every one of them, you'll find reverse engineering challenges. We had CTFs last night, and there were reversing challenges there. So typically, 48-hour event for kind of a global type of CTF, the ones that happen online. And the benefit of this approach is that all of a sudden it adds a time pressure to your reversing experience. And there's nothing like time pressure to kind of kick learning and your efforts in overdrive. So it really pushes you to learn more. The resource I recommend for that is CTF Time. Again, it's also a global directory of online CTF and sometimes offline CTFs. So if you go there, you'll see that every week there'll be several CTFs going on somewhere in the world, and you can just join and try it, and don't be intimidated. We've all begun at some point in the past, so there's no shame in losing in these or not being able to do even a single challenge, but it's a great way to learn. I find it extremely beneficial to my professional work as well. I learned a lot of new skills by playing CTFs, and it really pushes you, because if you're doing something on your own time, it's very easy to kind of slack out and not try hard enough. So I think time pressure is good. And they also have a global scoreboard for different teams. And then if you're feeling adventurous, if you're, you think you've mastered reverse engineering, there's kind of what I would consider a top competition in the world. And let me know if I'm wrong, if there's something better, but from what I know, it's the toughest challenge out there. It's an annual competition created by FireEye, which is a company that I believe it's a kind of antivirus type company. They deal with a lot of malware. And there are usually around 12 challenges of increasing difficulty, and you get 40 days to complete them. And that sounds like a lot, but from my experience, on some of the tougher challenges, you can easily spend a week or 2 weeks or more just on one challenge. They're really, really tough. The first one would be very, very easy. The very last one would be just a nightmare. And another great thing is that they have a mix of all kinds of technologies. Every year they add something new. So pretty much any platform you can imagine, they have challenges for that. They have challenges for compile stuff, for scripting, for mobile, embedded, various esoteric languages. They're not even kind of really languages that are used in real life. So it's really a lot of fun, and it's really, really challenging. Also, main challenges are based on real malware samples, because this is a company that fights malware. So this type of learning would be beneficial if you want to go into malware analysis. And the finalists get a prize, which is great, and it's actually kind of rare for online competitions. So if you want to get started, here are some strategies that I would like to recommend based on my own experience. So first of all, it can be a really tough challenge. Lots of attention to detail, takes a lot of time, so you better make it an enjoyable experience. If you're doing it because you have to, or you're not enjoying it, it's probably not worth it. You kind of have to get into that frame of mind that you will actually enjoy what you're doing. Otherwise, don't do it. You'll dread it. It requires a lot of patience, and you have to have some of goal that you're trying to achieve. You want to get that flag that you want to put on a scoreboard. You want to discover a bug. You want to find some kind of a hidden backdoor. So mental motivation is important. As you're doing reverse engineering, it's important to keep, quote unquote, keep your eyes on the prize. Even an average-sized application is really big. If you open it, like Windows Notepad has 13,000 machine instructions. It's unrealistic to fully reverse an average application. So be really focused on what you're trying to find. And honestly, even if you had fully commented original source code of an application you're trying to reverse, it will probably take you days and weeks just to understand it all. So don't make it a goal to understand everything. Focus on just specific things you're looking for. Combine static and dynamic analysis. I mentioned that before. Actively use debugger for analysis. Make the application do the heavy lifting. You can actually step through the code that, let's say, does encryption inside the application. Rather than doing things by hand, make that code do the decryption for you. And this thing is under your microscope. You are the master. you don't have to kind of make it, debug it all the way through. You can jump around, you can execute different pieces of code, do whatever you want with it, pull it apart, cut it in pieces and study pieces separately. You know, it's your game. You make it your own. And scripting some of the reverse work makes static analysis simpler. Scripting in general helps. When I do reverse engineering, I often write little scripts in Python to help me kind of decode things, decrypt things, and a lot of the tools come with scripting embedded. So that's use it. It's going to be helpful. You'll enjoy it more if you're more productive. As you do reversing, there are little bits and pieces of information that can help you if you find them. There are sometimes magic numbers. They're used in different algorithms. There are common algorithms that you can detect, let's say a hashing function, encryption function. If you search for certain signs of that happening, that can help you understand what the application is doing. There are specific system calls and library functions also that can give you clues to what the application is doing. And there are tools and plugins that actually help you find magic numbers, find library functions. For example, in IDA, there's a way to kind of detect library functions that were added to the code. I think that the final suggestion is document. It's very detail-oriented activity. There's a lot of information, and if you just look at stuff, you'll easily forget everything the next minute. So as you go along and you discover little pieces, add names to functions and variables, restore data structures and objects to their original form. There are tools for doing that in applications like IDA. Comment important code blocks. As you start doing that, you will see that things start to magically take shape. If you kind of do this in an iterative way, you will gain more and more knowledge about the application, and things will become more and more clear. It's really quite magical. So a few resources. It's hard to point to a particular kind of website where you can read all this stuff. There are lots of blogs, articles, so just Google it. There's a conference specifically devoted to reverse engineering that's incidentally happening in Montreal and also in Europe. So check it out. And also, if you need help, there are discussion boards dedicated to reverse engineering. So if you're stuck, just ask. There are a lot of books. They're available. I'll not kind of go through them. You can download the slides, and the links are clickable. Just something that can help you study. So to wrap up, there are a lot of software and hardware around us. Most of that is black boxes, but reverse engineering can help you look inside and understand how they work. You can help make these products more secure by doing security analysis. You can build compatible solutions. You can modify these products in new ways if you know how to do reverse engineering. There are plenty of tools out there that can help. You don't have to do it by hand. And as you learn more about it, I'm sure you will enjoy reverse engineering. It's really a fun thing to do and really intellectually rewarding activity. And that's it for me. If there are any questions, I'll be happy to answer them. But otherwise, thank you very much for listening.
Thank you very much for the question. Discord, like another conference. So if you want to get them there,
you're glitching, Philip.
I'm glitching. Oh wow.
Yeah, no issue. Yeah, if you can go on the Discord on the Talks Conf Q&A channel, that'll be awesome. Yep. And everyone can ask questions there. I don't think there was anyone left in the question.
No.
Yeah, perfect. So yeah, see you on there. If you need anything from us, just let us know, and everyone can also go into the Q&A. The next talk in 5 minutes. So see you everyone in there. Thanks again, Dmitry.
Okay, thank you so much. Okay, bye.